So I guess I'm all set and ready to get going on lab number one. So let's take a look. So I have my analog discovery 2 set up so that I can generate a power supply, although I haven't set the values correctly yet. And on the bench, I've got the AD2 is connected to my breadboard, and I've um, taken the power supply and moved it out to the buses so that the red bus is going to be my plus voltage, and the black bus is going to be my minus voltage. And so let's get started with the plan. I've got my notebook here, and let's see what we're going to do. So this is lab number one, and our goal is to build a series circuit, make voltage measurements, make current calculations, and measure resistance values, and by doing all of this, we're going to verify Ohm's law and verify, or maybe even we could use the word discover Kirchhoff's laws in the process. There's two H's in Kirchhoff's. Okay, so those are the goals. Write them down. Don't cheat. Okay, what do I mean by cheating? I mean taking a screenshot and just like putting it into your lab notebook. Not okay. Write them down. Same thing with the circuit diagram. So we're going to draw a circuit diagram. Everybody's going to have the same circuit diagram, but the uh, the values for the resistors will be different for you than they are for me. Okay, so we did this before. That's R1, that's R2, that's R3. This is our source voltage. The source voltage comes from the AD2. It's the AD2 positive supply, and we're going to set that to Vs is equal to 5 volts. Now, this is the ideal value, right? But um, in reality, it might be slightly different. So now current flows from positive to negative out of the supply and around the circuit. And so this is R1, and there's going to be a V1 across R1 with a plus to the left, and then a V2 across R2 with a plus to the top, and then a V3 across R3 with a plus to the right. There's so much stuff we could do in this lab because we have two ways of measuring voltages. We could compare those two ways even. Okay, so so here's our VS and our circuit, and we could label that I1 as the current going through resistor 1. I2 is the current going through resistor 2. I3 is the current going through resistor 3. Now, we could formulate a hypothesis here. And the hypothesis I'm going to put forward is that since current has to do with the amount of charge that flows through a component, the amount of charge entering the component is going to be the same as the charge leaving the component. So I'm going to say I1 is going to be equal to I2. And I'm further going to say that because the current entering R2 is the same amount of charge as is leaving R2, that I2 is going to be equal to I3. In other words, I'm going to say that the current through each component or each resistor is going to be the same value. And so lots of things we can do here. So when we measure the voltages, we're going to measure them like this. So I'm showing you with the DMM probes, but in fact, um, we may do this. We may do this with the DMM and the AD2, but basically we're going to try to do it all with the AD2 and take those values. But it'd be interesting to compare them. So that's how we measure V1. Red goes to plus, black goes to minus. That's how we measure V2. And then this is how we measure V3, red, black, okay? Now, there are other things we could define here. So we could define every point. So we could say this is point A, this is point B, and this here is point C, and we're going to call this point ground. So if we do that, then one of the things we'll be able to do to discover Kirchhoff's laws is to measure. So we're going to measure V1, V2, V3. We're going to use those to calculate I1, I2, and I3. And then we're going to measure VA, VB, and VC. And the way we do that is we use ground as our reference at all times, and then measure the voltage there. That's VA. Measure the voltage there. That's VB. And then measure the voltage there. That's VC. Okay? And then we're going to look at all the measurements and establish some rules. And we can establish rules for how voltages add in a series circuit and how resistances add in a series circuit. There is so much that we can do. Okay, so yeah, you didn't get that bottom piece, but there it is. Okay. Anyway, so this is the way I have my notebook set up. This is my plan. And so there's going to be a data table for measurements. And for calculated values. Okay. And so the things we're going to measure are R1, R2, R3, and then we're going to measure V1, V2, V3, and Vs, and then we're going to measure VA, VB, and VC. So we're going to record all of those, and then calculated. So not too much to calculate in the beginning. We're going to calculate I1, I2, and I3. And then we're going to look at the data and see if we can calculate VA, VB, and VC. Okay? Well, again, I went to the bottom of the page. So measurements and calculated values. Whenever we measure something, we use all the digits we can. Whenever we calculate something, we go to four significant digits. All right. So my notebook is set up. Here's my circuit board, and just a reminder of. Let's zoom in a little bit. Good. So just a reminder of what our circuit looks like. R1, R2, and R3, and voltage source, and this is going to be 5 volts, and actually we're going to measure these and we're going to know what these resistance values are. So and we're going to talk about them as ideal, and then we're going to talk about them as measured. So R1, R2, R3, and so this is going to be V1 plus minus, V2 plus minus, V3 plus minus. That's a terrible looking resistor. I got to change that. Okay. And R1, R2, R3, Vs equals 5 volts. Okay. So up here I have my 3 resistors. Now I can't see what the color codes are unless I bring my magnifier over. So excuse my magnification, but that's what we got to do. So I got green, brown, black, brown. So I got green, brown, black, brown. And so for R1, its ideal value is green is 5, and then a 1, and then a 0, And then brown is another 1, which indicates the number of zeros that goes after it. So 5100. So 5100, which is equal to 5.1 k ohms, and that's the way you should write it. Okay, 4 digits to the left of the decimal point, not okay. You need between 1 and 3. Okay, so that's my R1, and I'm going to immediately pick it up and stick it in my circuit where I think it should be, right there. Okay, so remember we set this up last time. Here's my positive voltage from my power supply. Here's my negative end of my power supply, which is ground. We would call that our reference or our 0-volt place. Okay, so there's my positive supply, and I've got my R1 in place. Now I'm going to take my R2. Here's my R2. And again, pull in my magnifier. And what do I see? So R2 is going to go like this. And what I see is looks like brown, black. It's either brown or red. Yeah, red, black, black, brown. Okay, so here I have a red, black, black, brown. So the way this resistor is marked, R2, red is a 2, black is a 0, another black is a 0, and then brown means 1 0 after that. So this is 2.0 k ohms. And just to be sure of these values, so let's take our DMM and check it out. So this first one's supposed to be 5.1 k. So I'm going to turn the range here to 20k because it's bigger than 2000. Okay, so next step up is 20k, and I hold that there and I see, oh baby, so beautiful. This is the beauty of 1% resistors, my friends. 5.1, just like it's marked. Okay, so 5.1k, no problem. Now let's take a look at my 2k. Now when I want to measure this, I definitely don't want it to be connected to anything else in the circuit. I'm just going to plug it into my breadboard here, put my probes across it. With any luck, it's going to be perfect like the other one. Let's see. Oh, I read that wrong, I guess. That first band wasn't red, that first band was brown. So this is 1k ohm. So I can get another digit of precision here by turning that down to 2000. 993 ohms. Okay, that's what I got. 993. So I need to fix this where I wrote red, that's actually brown. And that's not 2000. That's 1000, which means it's 1 k ohm. And but when we measured it, I've already forgotten what I measured. Let's look at it again. Now it says 994. I think it said 993 before. Okay, but 994. So how different is 994 from 1,000 ohms? Well, we could do a calculation. So on, and that would be, so the difference between 994 and 1K is 6. So it would be 6 out of 1,000, which equals that. And to get percent, multiply by 100 equals, so that would be 0.6%. So that's within the tolerance of the resistor. The resistor is 1% resistor within the tolerance. Okay. So that's R2. And let's put that where it belongs in the circuit now. So R2 is the one that goes vertically. Okay, so you see I have it plugged in there, in that hole. And so now my R3 is going to jump across there, so I'm going to move that over to there like that. So now here's R3, pull my magnifier over. Yeah. Yeah, this one's definitely red, black, black, brown. Okay. So this is red, black, black, brown. And so that's my R3. And so that should be red is 2 with the 3 zeros after it, 0, 0, and now brown means 1, 0. And so this is 2.0 k ohms. Let's put it in and measure it. So we'll just stick it down here, bring over our DMM, light it up for y'all. Okay, so if this is 2000, we're on the 2000 range. It might overrange if it's bigger than 2000. Let's see. It's not bigger, it's 1993. Okay, so this is equal to 1.993 k ohms. Okay, and if being off by 6 out of 1,000 is 0.6%, then being off by 7 out of 2,000 is like 0.3%, 0.35%. So that's perfectly fine. Okay, so now I'm going to move that resistor into position on the breadboard. And so positive voltage connected to R1, out of R1, into R2, out of R2, into R3, out of R3, and then to ground. And that's the whole deal. Okay. So let's set up now our analog discovery 2 to make some measurements. But before we do that, let me make some recordings in my notebook here. So my R1 is 5.1 k ohms, perfect. My R2 is 994 ohms, and my R3 is 1.993 k ohms. Okay, so far so good. So Now we're going to make measurements, and I need some, excuse my reach, need some wires here. So I'm going to take, I'm going to grab some of the longer ones. So here I got a long red one and a long black one. And so the long black one, now this, now up here, where we're only going to use channel 1 to make measurements. So let's get tight, a little tight here. Okay. So we're only going to use channel 1 to make measurements. And so the channel 1 minus side is grounded, but we don't want that grounded now because we need to use that as the negative probe. So I'm going to take my long black wire and connect it there. And now I'm going to take my long red wire here, and I'm going to connect it to the plus side of channel 1, and channel 2 is going to do whatever it does. Okay? All right. So let's make some adjustments here. Let's get a little wide. Get a little wide. Yep. Okay. So if I'm going to measure V1, I want my black probe on that side, and I want my red probe on this side. And I'll switch over to the screen and change the power supply to 5 volts. 5 volts. Turn off the negative supply because I'm not going to use it. And turn on the power supply. And then turn on the voltmeter. And this is saying 3.159 volts. So this is the value we're going to trust. 3.159 volts. And I'm going to make that entry in my 159 volts in my lab notebook. And now we're going to look at V2. And so let's switch over to the bench. So now to measure V2, we put the black lead the bottom of R2 and the red lead at the top of R2. And we go back to the screen view, and you can see that we have 614, 15, 14, 14 millivolts, 614 millivolts. So 614 millivolts is 614 times 10 to the minus 3 volts. Okay, let's go back to the bench and let's measure V3. Okay, so red probe, black probe, right? So now we'll go back to the screen, and the voltage is 1.231 volts. 1.231 volts in my lab notebook. And the last thing we have to measure is Vs. So back to the bench. So now Vs red probe goes up here, and black probe goes down here. And when we go back and take a look at what we got, I'm very impressed. So 5.002 volts. 5.002 volts. That is impressive. Okay, so put that in my lab notebook. And now we have VA, VB, and VC. So we're in the perfect place to measure VA. So for VA, the negative probe just gets stuck to ground for all three of those, VA, VB, and VC. And so VA, well, what do you know? VA is the same as VS, right? 5.002 volts. So now to measure VB, we just move this probe, the red probe, over to here. And we get 1.842 volts. So, oh, I'm sorry, I didn't show you that. So, bench view. So that's how you measure VB. So that's having the red probe here, point B, point A. So that's VA is from there to ground. VB is from there to ground. And now we're going to measure VC, which is from there to ground. So when we measured VA, we found out it's exactly the same as VS, measuring from there to there. So what do you think about measuring VC from there to there? Isn't that the same as measuring V3? It sure ought to be. Let's plug it in and see. So there it is, plugged in, and here's the screen view, and it's 1.231. Oh, but wait, I forgot to record VB. I've got to go back. VB in my lab notebook. 1.843. 43 volts. Okay. So now we can go down here to VC. VC, and this is 1.231 volts. Okay. So those are all my measurements. There you can see. Okay, so turns out that VA is the same as VS. And it turns out that VC is the same as V3. So awesome. Okay, so now since we have two ways to measure voltage, and I believe our trusted way should be the analog discovery. Let's take a look at what this meter tells us. So I'll put that on the 2-volt scale. I'll light her up. And already I'm not liking the 2 volts. Oh, that's a 2000. Yeah, oh, these are in millivolts then, if this is on the 2000 millivolt scale. Okay. So this is too big for that scale, so I've got to go to 20. And so red probe here, black probe here, and I see 3.14. It's going between 3.14 and 3.15. And in my notebook, that's pretty good. In my notebook, I had 3.159, so closer to 3.16, but that's not bad. Okay, so we have more digits with the analog discovery. That's and I think we have better accuracy with the analog discovery. Let's go on and take a look at the next one now. So the next voltage is less than 2 volts. So I think, oh, it's even, yeah, it's less than 2 volts. So I can put my red probe there, my black probe there, and measure this, and this comes out to be 611 and 611, 612. On the AD2, it was 614. Okay, and the last one, V3, I'll pull these probes out of there for now so we can have a clear view of what's going on. So touching to the metal, 1226 millivolts, which is 1.226 volts, and I had 1.231. So so this little meter's not all that bad. I'm going to trust what I get from the analog discovery too, though. Okay. So now let's take a look at what we do to calculate the current. So I think we're basically done with measuring now. So now it's all about calculating and verifying and learning stuff. Okay, so let's get a little wide here so we can see my lab notebook. So now we're going to be doing some calculations, and to do these calculations, we need to use Ohm's law. So do these calculations, we need to use Ohm's law, and so Ohm's law, V equals IR, but we want to calculate. Oh, you still can't see it, sorry. V equals IR, but we want to calculate I, so I is equal to V over R, okay? So I1 is going to be equal to V1 over R1, and I2 is going to be equal to V2 over R2, and I3 is going to be equal to V3 over R3, okay? So let's take a look. We plug in values now. So V1 3.159, 59 volts divided by R1, which was the perfect 5.1 k ohms. Okay, so if I'm doing this with my calculator, y'all can see it. Here we go. So this is 3.159 divided by 5.1 times 10 to the third. So that's 5.1 k ohms, and that equals that, but that's not in engineering notation, so we need to press the engineering button. And we get this, 619.41 times 10 to the minus sixth. So we're going to take this, we're going to take the most significant 4 digits from that. 619.4 and times 10 to the minus 6 is micro, and we're measuring current, so that's microamps. 619.41 619.41 microamperes. Our first lab calculation of the year. Awesome. Okay, so V2, V2 614 millivolts. 614 millivolts. Now, thing students always ask is, should I use the measured resistance value or should I use the calculated, the marked resistance value? Well, we saw that when you use this to measure voltage, you get slightly different numbers than when you use this. However, and those numbers, although we didn't actually calculate it, were probably within the 1%. For if we used the same instrument to measure both things, then absolutely. But here it's kind of a toss-up. To get practice calculating, I'm going to use the values we measured, though. Okay. So did I put those? Yeah. So 994 ohms, R2, divided by 994 ohms. So let's go. So now we have 614, and that's times 10 to the minus 3. And we're going to divide that by 994. And that equals 6.177, but we need engineering, 617.7 microamps. 17.7 microamps. Okay, and finally, the last one. Well, let's just make a comment about using this 994 here. So had we not used the 994, if we didn't use the 994 and we used the marked value instead, this would have been 1,000. And this number would have come out to be 614 microamperes, which is smaller than this. Okay, so already this is smaller than this. But our hypothesis says they ought to be the same. Let's go on to the last one. So R3 is 1.993 K. 1.993 K ohms, and the voltage we measured is 1.231. 0.231 volts. So using both measured values, we now do our division. 1.231 divided by 1.993 times 10 to the third ohms, and that equals 6.1766, but we need engineering units, 617.66 microamps. 0.6, so we're going to round this to round this up to 7. 617.7 microamps. Whoa! That's the same as that. The only one that's a little off is that one. And how much is it off by? It's off by 2 out of about 620. So 2 out of 620 is equal to that, times 100 gives us percent. So 0.3%, about 0.3% difference. And since our measuring capability is not that good, we're going to call the hypothesis verified. I1 indeed is equal to I2 is equal to I3. So, but this is only applies to a series circuit where the current flowing into one component is the same as the current flowing out. Okay. All right. So our calculated values: I1 619. We want to stick to 4 digits: 619.4. And 617.7. microamps. And this one is also 617.7 microamps. Amazing. Okay, are we done? No, we're not done. Because, so we have these three values: V1, V2, V3, VA, VB, VC, and VS. All of these things are things we measured. So V1, 3.159, V2, 614, V3, 1.231, 1 volts, and then VA. So VA 5.002 and VB 1.843, 3 volts, and VC 1.231. 1 volts, and VS was 5.002 volts. So a number of ways that we can look at this data. Let's look at the difference between VA and VB. So VA minus VB equal to 5.002 volts minus 1.843 volts. And we do this. So 5.002 minus 1.843 equals 3.159. 9. And we're subtracting volts from volts, so this is volts. I wonder if this corresponds to anything that's up here. Well, look at that. 3.159, 3.159. Coincidence? I don't know. Where's VA? VA is here and VB is here. And what we got was this voltage here by taking this voltage and subtracting that voltage from it. So let's see if that holds. Let's see if we get that voltage from taking that voltage and subtracting that voltage from it. So VB minus VC is equal to 1.843 volts minus 1.231 volts. That equals, this is exciting, 1.843 minus 1.231 equals engineering 612 millivolts. Wow, that's really awful close to 614. Awful close to 614. And of course, VC is equal to V3. So now what happens if we add up the voltage across each resistor? So this is called add up all the voltage drops. So the sum of voltage drops is equal to V1 plus V2 plus V3, which is 3.159 volts plus 614 millivolts plus 1.231 volts. Let's take a look. So 3.159 plus 614 millivolts is 0.614 plus 1.231 equals, oh baby, 5.004 volts. So the sum of the voltage drops is equal to Vs. And in fact, this is Kirchhoff's voltage law. Vs is equal to V1 plus V2 plus V3. So, boom. There you go. So that's lab one. Okay. Now you're going to do it with different resistor values. You're going to do the calculations. And hopefully, if you make your measurements right, you're going to come up with the same conclusions. Okay? There's a lot to do, right? I know. It's like, what, 3.5 hours worth of video to get you prepared for this. So honor my efforts and go forth and do well. And I'll see you in the lab.